Okay, this is section 8.4 and we're going to start mathematical induction. These are actually called induction proofs, and usually when kids hear the word proof they get a little freaked out. Induction proofs are really testing your ability to plug things in, if you can believe that. And so before we start that, to do that we have to master skills of substitution, being able to plug stuff in. So if this was the formula you were getting, or the little equation, could you find n of 2? And most of you could. You would write 3, you'd put a 2 there, you'd square it, and you'd minus 1. So you need to remember that the squared comes first, so 2 squared is 4, 4 times 3 is 12, 12 minus 1 is 11. Not so tough. If I asked you to plug in a p, most of you would write 3p squared minus 1, not too bad. When I ask you to plug in p plus 1, you'd probably go 3, p plus 1 squared minus 1. And if I asked you to FOIL that, I'm sure you could. You'd write it twice, and then we'd FOIL all this stuff together. Oops, 1. Distribute the 3, you'd have 3p squared, 6p, a 3, and a minus 1, and you could put those two guys together and make a 2. The whole point to, well, no, I shouldn't say that. The crux of doing an inductive proof is being able to plug in. So just remind yourself of that. Remember, I'm just trying to plug things in, and I just need to make sure I'm plugging things into the right spot. So these ones are just saying find p of k plus 1, so this is what we're plugging in for every p of k. So wherever there is a k, we're going to put a k plus 1. So k plus 1, and then in here there will be a k plus 1 squared. So wherever there is a k, I am supposed to be putting a k plus 1. So right there was a k, I put a k plus 1, and there's also that plus 1. And I'm just switching over to a pencil because I think it's bleeding through the other side. And so now we're going to simplify this. This guy is all in the power, so I can kind of work with what's inside first. So I get a k plus 1 and a plus 1, which is k plus 2 squared. And we would write that twice and then FOIL. So I'd end up with k squared plus 4k plus 4. So again, my job is just to plug in, to kind of keep track of what gets plugged in, and then simplify from there. The next one, p, k plus 1. So a k plus 1 goes right there. A k plus 1 goes right there. And I divide by 4. So it's a lot more stuff going on. A lot more foiling. And I'm going to save this one for the other side of the paper. We're going to do something like that where I've got 2 foils, and then we're going to have to FOIL all that together. It gets kind of cumbersome. Right now I just want you to focus on getting that k plus 1 in the right spot. Here's another one. Starts off with 1 plus 5 plus 9. I haven't hit a k yet. That's what I'm looking for. Because every time there is a k, oops, that's a 4. Every time there is a k, I am going to put a k plus 1. Minus 1, minus 3, plus 4, k plus 1 minus 3. So the trick is everywhere there is a k, being able to get that k plus 1 plugged in properly and not losing this minus 1, this times 4, all these other little bits that have to come along with it. Okay, so let's get into an actual inductive proof. What's that look like? There are a couple rules for inductive proof. I shouldn't say rules, but just ways to go about it that will make your life easier. And the way that I show you, the method that I show you, is how every inductive proof has to look. If you skip including certain parts, then it's not really an inductive proof. So the whole thing to an inductive proof is being able to prove that a particular sequence, like adding this up, doing a sum, almost sigma notation, doing this sum, will equal something. These all work. I'm never going to give you one that doesn't work. So your job is just to figure out how to prove that one side equals the other. So we start off kind of by saying, hey, I bet it works the first time. So if all I have is a 1, sorry, my pencil's in the way. If all I have is a 1, I bet that is equal to 1 squared. And it is. 1 squared is 1. And then the next pattern goes, well, hey, what if I do the first 2 odd numbers? Is 1 plus 3 equal to the second term, because that's what we're up to, first term, second term, equal to 2 squared? And it is. It's 2 squared is 4. If I go up to 3 terms, 1 plus 3 plus 5 is 9, and that's the same as 1, 2, 3, 3 squared. So this pattern of adding up odds and equaling that, however many you're going to add up, squared, we're just going to try and prove this. Our job is to prove that the left side equals the right side. And right now they don't. 1 plus 3 plus 5, all this stuff doesn't really equal n squared. We're going to try and make it look like that. So the first thing we do is we show that it's going to work the first time. And this will work every time. Again, I'm not going to give you proofs that don't work. So we're going to show that n equals 1 actually works as a step. So I'm just going to take my little formula and I'm going to plug in a 1. So 2 times 1 minus 1 equals 1 squared. So I get a 2 times 1 is 2, 2 minus 1 is 1, 1 equals 1. I did it. It's a big elaborate step. You're just showing that if I plug in a 1, it will actually work. Use the formula part only, not all this other stuff. This won't always be 1 equals 1. Sometimes it'll be 3 equals 3 or 10 equals 10. You're just trying to make them equal each other. So it won't always be 1 equals 1. But it will equal the other side. Next, if that works, and how we just kind of played around with this, and I showed you that the first one, the second one, the third one, I bet you can guess that the fourth one does work, and I'll bet the fifth one does, and I'll bet a whole bunch of them do. The concept of an inductive proof, when I tell kids about it, is it's kind of like dominoes. If you set up your dominoes and you set them up well, and that first one, as soon as you knock that first one over, what do you expect all the rest to do? You expect the rest to knock themselves over. So as long as that first one works, as long as that first one gets knocked over, then the others should work. So I'm going to assume that n equals k. I'm going to assume that it works all the way up to this number. Maybe that's 100 spaces in, 100 terms in. Maybe that's the 1,000th term along this little sequence. So 1 plus 3 plus 5 plus 7 plus ... And this step right here tells you what you're going to do. You're going to turn all the n's into k's. So I've got plus 2k minus 1 equals k squared. This is literally just a plug-in step. There is no math involved. You are taking the n's out and you're putting k's in. You're essentially saying to everybody, I bet that since the first one worked, I bet a whole bunch of them will. The crux to the proof, the meat and potatoes, is this next step. So we're on number 3. Show that n equals k plus 1 works. This is our job. So now we're going to prove n equals k plus 1. So everywhere there's an n, guess what we're going to plug in? A k plus 1. Now in order for all the dominoes to fall over, in order for this next one to fall over, let's say we were talking about 100. It's a nice good number. We went out 100 terms or 100 dominoes. If I want the 101st domino to fall over, we have to prove that it's going to work. So it's kind of like saying I'm going to set up all these dominoes. The first one's going to knock over. I kind of expect them all to fall over along the way. And if I want to prove that every single domino will fall over no matter what, that this will work no matter what, I go out there and I prove just one extra case. And if that guy works, then they're all going to work. If that one falls over, then all the dominoes will fall over. So 1 plus 3 plus 5 plus 7 plus ... plus. I need everything I assumed to be true. So I copy that much down. Then I add on, and this is the extra, then I add on my next term. If this is up to 100, let's just say, then this is going to be the 101st. So I'm going to put in a k plus 1. 2 k plus 1 minus 1. Equals, it also happens on the other side, k plus 1 squared. So I copy down everything I had to assume to be true. I need all that stuff to work. I need all these dominoes to fall over. And now I'm just going to prove that this one extra domino works. That this 101st or this 1001st term still works. And if it works in my equation, then I'm good to go. So now we have to let our algebra skills show that one side's equal to the other. Great. Now we have a fence problem. Nobody can jump the line. You will not be subtracting things from here over there. Once you draw that line straight down, everybody has to stay on their own sides because you're trying to prove that this side equals this one, so you can't move anything. So let's go with the easy side first. K plus 1, k plus 1. I'm going to FOIL that, get k squared plus 2k plus 1. So now my job is to get all of this stuff to look like that. So I got a little bit of work to do. We have already decided what 1 plus 3 plus 5 plus 7 plus ... 2k minus 1 is going to equal. We already decided what all of this equals, and we did it right above. We said that all of that stuff is going to equal k squared. So this is substitution. I'm taking all of that out and putting k squared in its place. Sorry, I wrote that down really low. K squared. Up above, we decided that 1, 3, 5, 7, all of this stuff would equal k squared. So I get to take it all out and put a k squared in its place. Plus, I still have this stuff. I'll just distribute this 2 to kind of simplify a little bit. 2k plus 2 minus 1. So this is what I've got left to deal with, and now the problem doesn't seem so bad. Putting these two guys together, I make the 1. And I got both of my sides. Sorry, my lights just went out. And I got both of my sides to equal each other. So you just did your first inductive proof. We're going to do another one. First step is always to show that n equals 1. So we're going to take just the formula part. Don't worry about this. We're going to take the formula part and we're going to plug in a 1. So 1 equals 1 times 1 plus 1 divided by 2. So this side's a 1. This side over here, I've got 1 plus 1 is 2, 2 times 1 is 2, and 2 divided by 2 is 1. So I did it. My first step works. Next, you're going to assume that n equals k. So you copy down everything, except where you find an n, you put a k. No big deal. That's a copy step. So far you're a couple steps into the proof, and we haven't done a lot of math yet. Next one, we're going to prove now that n equals k plus 1. So I copy everything I had. In order for this game to work, all the other pieces have to come along. And I have to put on my k plus 1 term. My extra term. My next one. Equals, I have to do the same thing on the other side. So k plus 1 plus 1 divided by 2. So this k is right there. That's all that stuff. Plus my extra. Then over here I got this k turned into a k plus 1 and this k turned into a k plus 1. Everybody got substituted. So now we already decided what all of this is going to equal. I'm going to take all of that out and put this stuff in for it. 1 plus 2 plus 3 plus ... plus k equals that stuff right there. And I have this, k plus 1, equals all this stuff over here. K plus 1, k plus, and I'm going to put these together, 2. And now we got our fence problem. Nobody can jump the line. And I got to get one side to look like the other. Out of these three terms, the only one that's kind of the odd duck out is this guy. He doesn't have an over 2 like these two. So I'm going to make him a common denominator, put it over 2. If I do that, I have to put a 2 on top as well. So I'm just going to do a lot of distributing. So putting this k in here, I get k squared plus k over 2. Putting this 2 in, I get 2k plus 2. And over here, foiling, I get k squared plus k, 2k plus 2. And I'm sure you can see now I've got a k and a 2k. This is kind of coming together. Common denominators, I can put them together all over one number. This 1k and this 2k make 3. On the other side, the same thing happens. The 2k and the 1k become 3k. And we just did another inductive proof. Your proofs have to look just like this. They have to have the show step. This is where you just use the equation part of the formula. Plug in a 1, show it works. Number 2, assume that n equals k. You have to write this. You have to tell everybody what you are assuming to be true. That 1 plus 2 plus 3 plus ... The whole thing, only everywhere there's an n, you're going to put in a k. This is the hardest line. Sorry, one more down. The proof step, you're going to copy everything you had and add an extra term. Add your k plus 1. So wherever there's an n, you're going to put a k plus 1. And you got to do that on both sides. That's the new stuff. For kids, the hardest part is remember to take all this out and put that stuff in. After that, it's a fence problem, usually a little bit of foiling, and some common denominators. Good luck.